Hello, everybody, and welcome to another great day of chemistry. So far, this chapter, we've looked at a lot of various systems with specific focus on non-reactive systems where we're looking at just expansion and compression of a system, as well as just simple heating and cooling. So these basic phenomena. But as we've noticed, there's a lot of conditions we have to worry about and whether things are ideal or non-ideal. So today we're just going to go ahead, take a moment, recap our major equations, as well as the major special conditions we've looked at. So one of the first things we really want to take a look at is what are our major equations? So good place to start with is we have the first law. So any changes in internal energy is going to be based on how much energy is entering or exiting the system. And this will either happen as heat or as work. And we can express most of that work in terms of PV work. Will be based on the change in volume, as well as the external pressure I'm working about, whether this is going to be the pressure applied to the system. So always keep an eye out for this. Now, the changes in internal energy, we have our nice general equation, which will be based on the intermolecular forces as demonstrated by the internal pressure and um, the isochoric heat capacity. And we have a similar expression for the changes in enthalpy, which in this case is really focused on the Joule-Thomson coefficient and the isobaric heat capacity. And if you have these, along with the corresponding changes in pressure, volume, and temperature, you can get most of your major changes in energy. We can also relate our internal energy to our enthalpy, remembering that the enthalpy is just simply the internal energy plus PV. Or in a derivative form, because again, we mostly care about changes, it's going to be related to the change in internal energy plus PdV plus VdP. With again remembering here that that P is really the external pressure. Now, these are our general equations that will hold for anybody, but we like to simplify our case where we don't have to worry about the messiness of interactions. So in these cases, we're often going to rewrite our equations for ideal gases. And for this, we have two major principles. So the first is we can relate our pressure, volume, and temperature with the ideal gas law. And again, we're mostly assuming closed systems where N and R are fixed. Then we have no intermolecular forces, which means both the internal pressure and the Joule-Thomson coefficient will both be zero. And we're often using this to greatly simplify our systems. So now let's go ahead and look at how our major properties are going to change in our equations for them under specific conditions. So we're looking at four specific properties we're often looking at: the heat of the system, the work, the internal energy, and the enthalpy. And we're going to be looking this under four major conditions: isothermal, so constant temperature; isobaric, constant pressure; isochoric, constant volume; and adiabatic. So this means no heat being transferred. So we're going to actually flip this on its head and start with this material we've covered most recently. So we'll start with adiabatic and work our way back to isothermal. So a good place to start on adiabatic conditions is simply the fact that, hey, by definition, an adiabatic system has no transfer of heat. Gotta love a nice definitional answer. Then we're going to actually jump down to the internal energy. So here we can use our general equation. The internal energy is going to be related to our changes in volume term based on the intermolecular forces and the change in temperature. But we can also express this for an ideal gas. And in an ideal gas, we don't have to worry about that change in volume term because the the internal pressure is zero. So in that case, the change in internal energy is simply just the isochoric heat capacity times the change in temperature. And we have our similar expression. The enthalpy can be just related to our general equation. But for an ideal system, Joule-Thomson is zero, so we're just based on the heat capacity. So this also is very useful because if I want to know the change in internal energy or the enthalpy of a system, we can often readily determine the heat capacities, and all we have to do is measure the change in temperature. Now the work gets a little bit more interesting. And here we can make use of the fact that if I have an adiabatic system, well, that means no heat is being transferred, which means the work is just the same as the internal energy. So we can use our internal energy expressions to describe the work in a system. So that means for a general system, if we know the change in volume and temperature, we've got the work. But for an ideal system, we can simply determine the work implied into a system by measuring the change in temperature. And this is really nice. Now let's work our way to the isochoric system. So for an isochoric system, let's go ahead and start by looking at the change in internal energy. Well, in this case, if I have no change in volume, then I'd start with this equation, but hey, dV is zero. So we're just left with CV delta T. And it is worth noting this is a general relationship. This will always be true under the isochoric conditions. But note for isobaric, the pressure still changes, so we're still left with the general equation. Or for an ideal system, we do get the ideal case. But again, note for an isochoric system with change in internal energy, this is going to be true whether I'm looking at an ideal gas, a non-ideal gas, or even a solid. The change in internal energy is just going to be based on the temperature. Now let's go ahead and look at our other systems. So remember, all of our work is PV work. And if V isn't changing, then it means we have no work. So an isochoric system no longer has any work being accomplished, which means our internal energy is rather nice and simple. It's just based on the internal energy. So we can figure out the heat for a system, whether it's ideal or non-ideal, will always be based on CV delta T. Now let's work our way back to isobaric. So in an isobaric case, if we're looking again at the change in internal energy, unfortunately, we're left with the general definition. But if I have an ideal gas, I get to ignore that attractive component, and we are just left with the CV delta T. Whereas if I'm looking at the enthalpic term, notice the general component has a change in pressure, that's zero. And so whether I've got an ideal or non-ideal system, either way, enthalpy is just Cp delta T. And that is really pretty. Now, if we make our way to work, again, assuming the isobaric conditions, we're looking at external pressure, then we get one of our favorite equations. The work is simply PV dt dV, which often integrates to P delta V. So again, that's a really nice, pretty equation. And on the heat term, here we get to take advantage of the fact that, as we've seen previously, whether we're ideal or non-ideal, enthalpy will still be, the heat will be equal to the enthalpy, and that's just Cv delta T. So we love that. Now the isothermals, again, the place I really started, but now we can look at it for a non-ideal system. And this actually gets really fun when we look at the internal energy and enthalpy. Because here we see that if we look at the general equation, both of these forms have these dt terms, and that will drop to zero. That means the enthalpy under isothermal conditions is just based on the intermolecular forces term. So it's just going to be based on the Joule-Thomson and the change in pressure. But that also means that under an ideal case, that just drops out. So for isothermal gases, for ideal gases under isothermal conditions, there is no change in internal energy or enthalpy. But under non-ideal systems, any change will be based on these intermolecular forces terms. Now, if we're going to look at our good old friend work, this is just pressure, the external pressure times dV. The problem here is we now no longer have a way to simplify that pressure expression, which we had for all three of the other cases where I got to simplify the dV by dropping it out, or the pressure. Here we have no luck. So we're left with the general case. But if it's reversible and an ideal gas, again, both of those things must be true, then I can go ahead and replace it with our friend nRT with the natural log of the ratio of volumes. Note, this doesn't just require ideal gas, this also requires reversibility. Now, similarly, the heat, okay, here we can go ahead and relate the heat to the changes. We can relate the heat here both to a combination of the intermolecular forces term and the work, which again, because again, this is just du minus pdv. For an ideal gas, we can go ahead and ignore the intermolecular forces, and the heat is just going to be related to the work because remember, the internal energy has dropped to zero. So notice there's a lot of cases, but in each of these cases, we're deriving it from those 3 or 4 main equations, and we're just finding our ways to simplify. So you can go ahead and try and memorize all of these special cases, or just memorize the handful of equations on the previous slide and make sure you got good practice simplifying. Either way, best of luck. And next time, we're finally going to talk about chemical reactions. Until then, take care.